Healthy soils are essential for achieving broader goals, such as net zero carbon emission, reversing biodiversity loss, and sustaining human health. But to fix our soils, we must first understand them. We need tools to identify quickly the land that is being degraded and needs our attention. Then policymakers can target those areas with policies to promote sustainable land management and farming practices. For this series, we are interviewing some of the leading scientists who are working to create these tools. They are part of the project funded by the European Union called AI for Soil Health. And as the name suggests, they are using artificial intelligence and a range of other cutting-edge innovation to lead the way towards understanding our soils. In this episode, we hear from Sonia Meller, co-founder of DigitSoil. Welcome on our podcast, Sonia. And I would like to start with a question on soil biology. So soil biology has been overlooked for a long time. Why do you think that is? And how has this lack of knowledge impacted agriculture?
Hello, thanks for having me. It is quite interesting if we think about soil biology, because that's really the notion now that we are opening the soil biology as a new thing. But if we look back, people are always thinking of soil as a living thing. And if you look at the late 1800s, there's been already some foundation for soil biology. Even Charles Darwin was researching earthworms. There was this notion that we should look into a soil biology. And I think people working with soil and farmers understood it's a biological systems. But then I'm sorry to go a little bit into philosophy/economical perspective on things. We went as a civilization into this high productivity extraction philosophy where we focus on production and the highest productivity possible with Industrial Revolution and then Green Revolution. The notion became that we should just fertilize soil a lot to get as much as possible as output. So productivity and yield were in the focus. And at that early stage where the soils were still not that degraded, just adding fertilizations and producing food was a good strategy to obtain high yields, to just feed growing populations. But as we learned with time, for the last 40 years, there's been an emerging trend in understanding that soil is not only the mix of chemicals and minerals, there are processes that govern it, and that the soil is being degraded over time due to our management practices that are basically extractive. People started to look into it. Farming started to be more conscious, and we started to think about how we can actually protect our soil so we can keep our production instead of losing it like it's happening now.
Yeah, and opposite to degraded soil, we also hear the soil is alive. But what does that actually look like? And where do enzymes fit into that picture?
Yes, soil being alive is a beautiful picture. I think there's a lot of pictures on the internet with things living there and doing things. But how I like to think about it is that if we generalize, living things are reactive. So if you do something, they would react. They are living organisms in the soil, and how we know they are there is because they do something. There are different things in soil. If you think about living things, there will be roots of plants that grow into it. They are alive very much, and they attract other things. Everybody's seen earthworm. But there are also, of course, fungi and bacteria, and they are very small. We cannot really see them, so it's very hard to imagine. But they are there, and the interesting things about them is that we cannot really very well predict what they do. So we have pretty good models for soil chemistry and soil physics. We know if you press the soil very much, it will compact, and it will be very hard to plant anything on it because it will be squeezed into a block. So that's soil physics. With soil chemistry, we know a little bit if you put certain fertilizer and there's rain, it will be washed away, or if there is sandy soil around. We know that there are models around. But for living things in the soil, they will not only react, they will also adapt. And that's the big thing. A very famous way of experimenting with microbiology is you grow your bacteria in a little bowl and you feed it something, give it sugar, and it will grow, it'll be happy. And then you cut the sugar and you give them something else. These bacteria would either switch their way of obtaining nutrients. So they will switch their metabolism and try to eat something else or die off. And there will be new bacteria coming in their place. That's the difference between the soil chemistry, physics, and biology. And that's what makes living things such robust, interesting systems that drive soil and agriculture, is that we can train them to do things and we can observe what they do and use it for our advantage. There are famous examples of using soil biology and understanding it in the soil that helps us. For example, nitrogen fixing bacteria. Nitrogen is very important. It's the most important nutrients for farming. You always have to have nitrogen in the system to grow anything. But it's very expensive for humans to produce fertilizers with nitrogen. We use energy to do it. But there are also bacteria that can do it for us. Using them can save us a lot of money, a lot of effort, and a lot of pollution. I like to think about it more like it's something that reacts and adapts, just like us.
Thank you. And how is testing for enzyme activity different from the standard soil tests farmers already use for things like nitrogen or phosphorus?
Yeah, here we come to the enzymes. So normally you would go and take the soil sample and send it to the laboratory, and they will send you results back, and they will tell you your soil has this much nitrogen, that much phosphorus. When we measure enzymes, these living adapting things, part of their adaptation is production of these enzymes in the soil. And what they do, they help every living thing in the soil to obtain food. They would cut anything complex in the soil into simpler things and then allow them to grow. And when we bring that measurement to the farmers, what do they get? They don't get how many bacteria there are, they don't get how many roots there are, but how fast the soil is releasing their nutrients. They can calculate, or we can calculate, how many nutrients is coming from the soil. When we want to grow something, we can measure it in the soil, and then we get the rate. So per day, you are going to have this much nitrogen for your plant. And then we can ask how much your plant needs at this point. And if the soil is providing enough, then we are good. We don't have to do anything. We saved money. We don't have to drive. We don't have to buy anything. We have to do anything. But if we say, oh no, this is a really critical stage of plant growth. The plant needs twice as much as your soil can provide. Your soil cannot do this. There is not enough material in your soil to provide enough nutrients. You will have a really bad harvest. Then we can calculate that difference and just say you have to add this much fertilizer to top it up to meet your target. So you can still make money because farming is a business.
Can you walk us through the technology you are building and what it could mean for farmers and others who work on the land?
It's actually quite exciting. I've been working on it with my colleagues Jasmine and Helen for a long time. When I spoke about measuring enzymes and how fast things are being released, it is very complicated biochemistry. You need good equipment for it, and normally laboratories would do it. But what we were thinking, how we should make it accessible and useful, is to make a device that is easy to use, so you can actually do it yourself. We design a machine in which you have to take the soil from your field. For example, we can think of maize. It's now spring, and in the northern hemisphere, soon we will be planting maize or corn. You go to the field where you plan to do something, you collect the soil, and you put it in a little box. The procedure is easy. Take your soil, you put a little vegan cheese, if you like, so our special reaction plate on top, and you put it in a little machine. You put it there, you start it, and it's done. Your work is done. You can go for coffee for 1 hour where the machine is analyzing your soil. And after that, you have your information on what is the potential of your soil to release nutrients. And then we harvest this information together with your location and the climate you have and the current weather, and we compute for every day how many nutrients your soil is capable of releasing. And if you then give us information of what plant you want to grow, what yield you want to target, we combine all this information into a very specific timeline that is adaptive based on the weather. This is the ability to understand how fast nutrients are being released is very useful to make your calendar. So you can match the plant needs with your soil provision of the nutrients and reduce the losses. So that's a very big thing about understanding how much your soil is releasing, because your soil is releasing a lot, or if your soil is not holding into nutrients very well, then you can put a lot and still get a bad yield and then pollute the local groundwater. And we know high levels of nutrients in the water are not healthy for anybody, including ourselves.
That's true. And in practice, how could a farmer actually use enzyme data? And could it be a game changer for regenerative agriculture?
I think it is very interesting for regenerative agriculture, especially because regenerative agriculture very often relies on organic inputs and certain practices on cover crops and growing one plant after the other, so the previous crop provides nutrients for the next. This is much more tricky to understand how much is coming from these sources to the soil and from the soil to the crop than if you says put 100 kilograms of N per hectare, because it's chemical fertilizer. It's a simpler structure and it's immediately there, versus something that releases nutrients over time. So their enzymes are especially important to understand the nutrients going to the soil and to your plants. For that specific example, have our device and measure your enzymes, and then put a little bit of background information into our model and obtain really straightforward instruction on why and when you should fertilize. Just measuring enzymatic activity or how fast nutrients are being released, it's not enough. You have to put in a context, undergo thermodynamics processes. So if it's warmer, your potential of nutrient release will be higher. They will be doing everything faster. If it's very dry, they will not be able to move around, so they will not release as many nutrients as we would expect. So one number will not tell you much. You have to really go throughout the season in a context.
Looking at the policy side, how might policymakers use this kind of data? Could it fit into something like the monitoring law?
I would very much hope that it should fit into the soil monitoring law. I know so far it is not there, but there is a lot of room to grow the biological part of the soil monitoring law. I think enzymatic activity could fit there very well because it's a very functional parameter. Like I was explaining before, the organisms and ecosystem is adaptive, so they can change, but the function may remain the same. So if you want to monitor how active your soil is, if there's a major change due to the climate, to the ability of your soils to provide nutrients, this is the parameter you want to measure. You may not see the change in biodiversity, for example, but you will see that there is no mineralization, there are no nutrients being released. So, okay, the soils are maybe getting too dry. We have to do something, we have to change management. That would be on the general level, but the monitoring law is just for monitoring, and there are also lower level of laws that look into the soil and regulations. And I think measuring and looking at soil biological indicator in the form of soil enzymatic activity would be very interesting for local governments to monitor the risks of nutrient losses and regulations on management practices to actually help to prevent pollution locally and to tighten the nutrient cycles, so we can really apply nutrients when they are needed and reduce as much as possible the pollution to the air and water.
So, a last question. If every farmer in Europe woke up tomorrow with access to this biological data, what might the countryside look like 5 years from now?
That's a beautiful picture. There is a lot to do in general. How would the countryside may be the same, but everybody would look a little bit happier? Because it is difficult to see what's in your soil and what to do there, and that is quite a big dose of anxiety and a bit of guesswork. And there are a lot of regulations coming at everybody from every side. I believe if we could have easier access to information on how you actually do things and be able to translate it to something that is not scientific jargon. So we're not speaking soil enzymatic activity, mineralization, and all this terminology, and we say your soil can give your crop only this much and you have to top it up like this, then I would expect it to be a little bit more relaxed and hopefully also more financially stable.
Yeah, that's not a bad idea either. Thank you so much, Sonia. Thank you for sharing your knowledge and experience on the podcast.
Thank you very much. Bye.
AI for Soil Health is funded by the European Union and has received funds from UK Research and Innovation under the UK government's Horizon Europe funding guarantee. For more information, visit aiforsoilhealth.eu. That is AI for as number soilhealth.eu.